In our final section, let's now look how different pieces of spectral information combine to give rise to something that allows us to interpret the structure of even an unknown compound. So let's look at a compound which has higher absorptions at 30-30 reciprocal centimeters, and this is a medium absorption, as well as another one on 20-80 reciprocal centimeters, which is also medium. In addition to that, we know that this compound has a mass spectrum with two peaks as highest mass peaks, 170 and 172, and they're a ratio about 1:1. And its NMR spectrum has three main peaks. There's one at 7.8 ppm, and it integrates for 2. Another one at 7.3 ppm, it integrates for 2 as well. And finally another one which integrates for 3 and is a singlet at 1.3 ppm. What is this compound? When you look at this combined information, you need to be relatively organized in the way you approach this problem, because there are a lot of organic compounds, and simply guessing will not get you very far. So what you want to do is probably try to identify the simplest piece of information, which will then get you started, and from that point you start making certain deductive steps until you get to your structure. In this case, one thing that is very indicative is this presence of two mass spectral peaks, which are separated by two mass units, and they're an exact ratio 1:1. This almost conclusively indicates that you might have bromine in your molecule, because we mentioned that bromine has two isotopes which are separated by two mass units and which will give rise to these. And indeed, if we make this assumption we have bromine in there, then by subtracting from 170, subtract the mass of the lower isotope, which is by the same equivalent as subtracting the mass of the higher isotope from 172, we will get the remaining mass in our molecule, which is 91. So now we have to account for 91 mass units in our system. Okay? Now, looking at this region of our spectrum is also quite indicative, because this is between 7 and 8 ppm, and these are typically aromatic protons, which indicate that we might have some sort of a benzene ring here. Okay? The mass of benzene ring is 78, but since we'll probably have it substituted maybe here and somewhere else, we should probably be looking somewhere in the 75 to 78 region to establish what we have. And if we see that there's 75 to 78 here, and we subtract that, what must be left is something between 16 and 13 in mass. Now the question is, well, what could that be? Okay? We don't know at this point, and so to answer this question we need to look at the remaining pieces of information. If we look at our IR spectra, we see two main vibrations. This vibration is coming from the CH bond associated with the sp3 carbons, while this one is coming from the CH bond associated with the sp2 carbons. Now this one we already knew about, because if we assume that we have a benzene ring in there, then of course we'll have some sp2 carbons, and this is clear. But this seems to tell us that we can have an sp3 carbon here as well. And this is important because we didn't know this so far. The simplest sp3 carbon would simply be a methyl group. And in this mass, which is all that we have left to manipulate, we can really not fit much more than a methyl group anyway. So it seems like our molecule is composed of methyl group, some sort of a benzene ring, and bromine in some sort of arrangement. To figure out this, which exact arrangement that we're having, we need to go back to the proton NMR spectrum. Proton NMR will first confirm that we have a methyl group, because we have this rare integration of 3, and also that this methyl group is a singlet, which means that it's not attached to anything else. Okay? Now, it means that it's not attached to anything else that has protons in it. So it could be directly attached to the benzene. Okay? Now, where do we attach the bromine to this benzene? Well, we could attach it to the ortho position, but that would give rise to 1, 2, 3, 4 different kinds of peaks. So that's not what we're seeing here. We see just the two doublets, two different kinds of proteins. If we attach it to meta position, again, we will see 4 kinds of peaks. But if we attach it to para position, then we will see just 2 kinds of peaks, because we'll have 4 hydrogens. These 2 will be equivalent as well as these 2. And they will couple to each other, causing each one of them to become a doublet. Which means that this is the final structure of our compound. As you've seen, there were a lot of rational elements in this analysis, but at some point I made pretty much leaps of faith, which I had no real justification for. And that is fine, as long as you can make leaps of faith in your analysis, as long as you establish a structure after the leap of faith, go back to the data and confirm that that structure is correct. If your data does not support a structure, then it's wrong, and you need to move on and find a different one. But that is sort of a thought process that I would suggest to analyzing these spectra, and that is that we start with the simplest pieces of information we can extract, get a couple of quick bits together, then from there see if we can easily rationalize something else, get a couple of more bits of information together, and then put together a structure. Some part of that structure will be guessing. A large part of it will not be guessing because you'll have this information. But the part that you guess is fine, as long as you now go back and confirm or dispute that guess by the remainder of information. At the end of the day, all the information has to support your structure, and if we have any exceptions, then it's very likely that you're wrong. With this, we'll finish today's lecture, and in our final lecture of the course, we will talk about the carbon-13 NMR spectroscopy, which is another layer on the cake, if you want, of structural information that we can get from spectroscopy that allows us to predict and propose structures of unknown materials. Thank you.